So, in this problem, I've got a tree branch that ends up falling on a wire that's separated by a post. The tree branch lands a fifth of the way across on one side, and the distance between the two posts is 4 meters. So it looks something like that, okay? So we know that this distance is going to be 4 meters. Okay. We know also that the depression here from the problem itself is 0.2 meters. Okay. And we also know that the tree branch is a fifth of the way through. Using that, we should be able to calculate all the angles that we need to know right off the bat. So looking at that triangle, what I'm going to do. Okay. Looking at the one triangle, this is going to be 1/5 of 4 meters one way and 0.2 meters this way. Now, you can use 0.2 and think of it as a fifth if you want to, but it doesn't really matter. The other way is that we got over here, this triangle is going to be 4/5 of 4 meters. And it's going to be a 2-meter depression. Okay? With that information, I have the opposite and I have the adjacent. I have the opposite and I have the adjacent. So I'm looking at a tangent. Tan theta 1 and tan theta 2. There's no way that these two angles are going to equal each other. The only situation where those two are going to equal each other is if this object lands directly in the middle. Okay. So tan theta 1 is going to be opposite over adjacent, which is going to be equal to 0.2 divided by 1/5, or why don't I just multiply that across, 4/5 meter. Okay? This is a meter. While over here, I'm going to end up with opposite as being 0.2 meters divided by 16/5. So there's my answers. That gives me the angles, and now these angles are going to be really critical in order to solve the tensions of those wires. So I'm going to go ahead and write these up here and then erase the board and do the rest of that problem. Okay, so there's my angles, there's my diagram, and now let's look at forces. Okay, looking at the free body diagram of that tree branch, okay, we have the weight down, and we have a portion of the tension up. Let me move that over so there's my tree branch. We have the weight down, and then we have two vectors up. Well, let's make the weight a little more. There we go. Okay? So that the length of this vector is equal to the length of this vector plus the length of this vector. And actually, it's going to look like that. Cool? Okay? Also, in this direction, I have one tension and I have another tension, and because the object's not accelerating in this direction, these are equal to each other, which is going to be critical. Okay? So what I can do is I can say that, I'm going to write over here, the tension 1, which is this side, we'll call this side 1, and this side 2. The tension direction, 1x is equal to tension 2 in the x direction. So tension in the x direction this way is equal to the tension in the x direction this way. If not, that log is going to accelerate one way or the other. Okay? So these two tensions have to be equal to each other. Well, if I want to determine this component of that tension, I'm going to be left with T1. Instead of talking about x, I'm going to be talking about the cosine of theta, and that's theta 1, is equal to T2 cosine of theta 2. Okay? Cool? So that way I can then say, well, T1 cosine theta 1 by theta 2 is equal to T2. Okay? So I have this solution where I'm relating tension in this direction to the tension in this direction. Really, so I have a scaling factor. This is just 2 times as large, 4 times as large, half as large. So that's all it's going to do. It's going to scale it for me. What I need to do is be able to add the weight into an equation, because the weight I have a numerical response for. And so what I can do there is say that the tension in the y from 1 plus the tension from the y from 2 is equal to the weight. Oh, ran out of space. Tension 1 in the y plus tension 2 in the y is equal to the weight of the log. Okay? And then do a little T1 sine theta 1 plus T2 sine is equal to mg. Okay? From there, I'm going to have to give myself a little more room, so I'm going to erase the free body diagram. From there, I can substitute T1 cosine theta 2 equal to 2. So I can say T1 sine theta 1 plus T1 cosine theta 1 cosine theta 2 times sine theta 2 is equal to mg. Okay, so that's T1 sine theta 1 plus T1 cosine theta 1 over cosine sine theta 2, this equation, times sine theta 2 is equal to mg. So then I'm left with T1 sine theta 1 plus T1 cosine over, or sine over cosine is tangent, so I'm left with tangent 2 cosine 1 is equal to mg. And I know that tangent of 2 with this, we'll make this 10, I'm just right out, 0.2 over 16 fifths. Okay? And then from there you have this sine and this cosine. You'll have to solve for this angle in tangent by using the inverse tan. So you can say theta 1 is equal to tan inverse of 0.2 over 4/5. Solve for that theta. Plug in those thetas. You know this. You know this. And you know this. Leaving you only with T1. Once you solve for T1, put it into here and solve for T2. Okay? So that's how you solve the tree branch problem.